Okay. Okay, so here's the Zoom meeting. Okay, so here's the Zoom meeting for Physics 231C. Can you hear me? This will be our regular time, Friday afternoon at 4 p.m. Earlier this week, we had a Zoom meeting where we went over these things. So that was the previous Zoom meeting. We looked at Lon Kappa, the syllabus. So you should already be familiar with lonkappa.msu.edu. That's where you'll find all the assignments. Eventually, that's where you'll find the exams. Now, for today, we want to. All right, so this was the earlier Zoom meeting, already did that. Here's today. You've been reading chapter 1, and there's a short quiz about chapter 1, which is due tonight. And then the first problem set will be due Tuesday, which will be on problems from chapter 1. So the main thing for today is to look at a couple of the problems from problem set 0 and provide some hints and explain how those problems should be done. This is next week. Monday is Labor Day. Tuesday is the due date for problem set 0. And that'll complete chapter 1, and you'll start reading chapter 2. Now, there's something important on Wednesday. That's the pretest. So the pretest is important. That'll earn you points for the final grade. It's 70 minutes long. You have to do it all in one sitting. So sometime when you have 70 minutes free, you can do the pretest. It has to be done by the end of Wednesday. I think it'll open earlier, so you'll have several days to work on it. It might already be open. I'm not sure about that, but anyway, it'll be at the Lon Kappa site, and you'll just see pretest. So you have several days when you can do it. You don't have to do it Wednesday. In fact, you're probably better off if you do it earlier. So, you could do it Labor Day, for example. Anyway, get it done by the end of Wednesday, and you have to do it all at once. And then reading quiz 1, the next reading quiz will go along with chapter 2. And we'll have another Zoom meeting Friday. So these are the assignments for next week. And then the following week, you have to turn in the problems for chapter 2. That's problem set 1. and go on to chapter 3. And so on until we have the exam the last week of September on Tuesday. When you're reading the chapter, you should take notes. Each chapter is about 30 pages, probably a little less than 30 pages. You should be able to read the chapter in 3 hours. You don't have to do it all at once. Do a few sections one day, a few sections the next day, a few sections the next day. Spread it out over several days. But as you're reading it, take notes in your physics notebook. You should have a physics notebook or maybe a 3-ring binder, which is only used for physics, and take notes as you read the chapters. So for each chapter, you should have about 1 page of notes, front and back, which are the important equations in the chapter, because you're going to have to use those equations to do the homework problems. Now, chapter 1 is about measurements, and this is something you've probably studied before. You have to learn the standard units that we use in physics. The basic units are mass, length, and time, and we use the units of measurement, kilograms, meters, and seconds. Then there are SI prefixes that you have to know. Kilo for 1,000, so a kilogram is 1,000 grams. Mega for million, so 1,000,000 meters is 1 megameter, or 1,000 kilometers. Micro for 10 to the minus 6. You also have to understand how to convert between units, like the old English units that we use in America, and the standard scientific units. There's a section on dimensional analysis, so you should understand how to analyze dimensions. That tells you how to determine the units for the LON-CAPA answers. I've noticed on the LON-CAPA discussion board, a lot of people are asking questions about what's the correct unit. Well, you understand the unit by just analyzing the dimensions of the quantities that are used in the calculation. So you should know how to calculate numbers with units. You have to carry the units along with you in the calculation, treat them as algebraic quantities, and then the final result of the calculation will have a unit with it. So you'll immediately know what is the correct unit. You won't have to put the question on the discussion board. Also, I've noticed there's some questions about significant figures. An answer in LON-CAPA, an answer in a physics problem, is usually a number with a unit. You have to know how to calculate the units. Well, just look at the units that you're using in the calculation and combine them using algebra, and that'll tell you the unit of the answer. As for the number, your calculator will give you 10 significant figures. You don't want to write down 10 significant figures, and LON-CAPA won't accept 10 for significant figures. Most LON-CAPA answers are going to be in 3 or 4 significant figures. So, just give 3 or 4 significant figures unless the problem says to do something different. In particular, 1.00 is not the same as 1. To a mathematician, these are equal. But to a scientist, these are not equal. 1 is an integer. It's an exact number. 1.00 is an approximate number with 3 significant figures. It could be 0.999. It could be 1.001. those are both the same as 1.00 to 3 significant figures. And I've noticed again on the discussion board, some people are having problems submitting answers with an appropriate number of significant figures. Don't use all the numbers, don't use all the digits from your calculator. That'll be too many significant figures. All right, so that brings me to some example problems from problem set 0. That's the problem set that's due next Tuesday, the day after Labor Day. These are problems which come from chapter 1. So you should have already read chapter 1 by now. You'll be familiar with these problems. Some people have already started doing the problems for problem set 1. But let's go over a couple of examples and just see what's involved in solving a problem on ln kappa. So here's the problem statement in ln kappa. Approximate Saturn as a sphere. Planet Saturn. Ignore the rings. Say it has mass m and radius r. Calculate the mean density, that's part A. Compare it to the density of water. That's part B. Now, the problem doesn't tell you the values of m and r. So one thing you'll have to do is look up the mass of Saturn, m, and the radius of Saturn, r. You have to look them up someplace. You can look them up in Appendix E, which has a bunch of, which has a table of values relevant to the solar system. However, it turns out the value of m in Appendix E is wrong, so don't use the value of m that you find in Appendix E. Instead, do a Google search. Just type into Google, what is the mass of the planet Saturn? And Google will return you an answer, and you can trust that. And do the same thing for the radius. Again, you can look up the radius of the planet, and you can find the value in the appendix. Actually, the value in the appendix may not be accurate, so you can try a Google search instead. You should get the same number from either the textbook or Google. But if there's an error, it's more likely to be in the textbook than it is in Google. Now, in many problems, the first thing to do is draw a picture. So suppose we start this problem by drawing a picture. Well, we're talking about the planet Saturn. Saturn doesn't have a particular color, so let's just make it black. Here's the planet Saturn. Now, you know it also has rings. Well, that's not a very good circle. I mean spheres. Let's see if I can draw a better sphere. So there's Saturn. It has a certain mass. That's the total amount of material. And the standard unit of mass is a kilogram. So that'll be a number with a unit. And the unit is kilogram. And you're also going to need the radius. So in your picture, draw this picture in your notebook before you start the problem. Radius is the radius of the sphere. Now the question is, what's the density? So you have to know the meaning of density. That's explained in the chapter. Density is a good example of a ratio. Density is the ratio of mass divided by volume of some object. In this case, the object is the planet Saturn. So density, we usually use the Greek letter rho to stand for density, is m over v. Now, m you looked up in Google. V is the volume of a sphere, and you remember from high school geometry, the volume of a sphere is 4/3 pi r cubed. So if you know r you can calculate V. Now, when you calculate the density, you'll divide M by 4/3 pi r cubed. That'll be a number with a unit. So the answer will be a number with a unit. Let's figure out the unit first. Well, the numerator here is kilograms, and the denominator is cubic meters. So the unit of mass is a kilogram, the unit of volume is the cubic meter. So the unit of density is kilogram divided by cubic meter. So that takes care of the unit. Now, what about the number? Well, you look up the mass, it'll be something like 5.6 or 7 times 10 to the 26 kilograms. In the denominator, we have 4/3 pi. We'll have 58,000 kilometers cubed. Now, we'll want to convert this to kilograms. Well, the numerator is already in kilograms, so I don't have to do anything to the numerator, but we'll have to convert this to meters. A kilometer is 1,000 meters, 10 to the third meters. To the power 3, 10 to the third to the power 3 is 10 to the power 3 times 3. 3 times 3 is 27. So of something of the order, so just doing it approximately, of something like 6 times 10 to the 26 kilograms in the numerator, 4/3 pi is about 4. I got to be a little careful about the unit here. Let's say I have 10,000 here. I have actually 50,000 here. So let's figure out what the unit's going to be. It's going to be something like 10 to the 4th kilometers. So that's 10 to the 3rd. So I can write that as 10 to the 4 plus 3. That's 10 to the 7th to the power 3. So that's 10 to the 21. So it's going to be something like 10 to the 21. Now you can do this more accurately with your calculator, or you realize that 5 cubed is going to be another couple of powers of 10. So instead of 10 to the 21, I might have more like 10 to the 24. If you do this carefully using your calculator, find it's about 0.6 times 10 to the 24, and the unit is cubic meters. So now if I look at the powers of 10, 10 to the 26 over 10 to the 24 is 10 squared, and 6 over 0.6 is 10, so it's about 10 cubed. So it's about 10 cubed kilograms per cubic meter, about 1,000 kilograms per cubic meter. Well, that's just the order of magnitude, but you'll have to calculate this accurately with a calculator. Now, it turns out the density of water is 1,000 kilograms per cubic meter. 1 cubic meter of water, imagine the size of 1 cubic meter, 1 meter by 1 meter by 1 meter, a big box full of water would weigh 1,000 kilograms. That's a metric ton, weigh a metric ton. Well, the density of Saturn is about the same. The density of Earth is about the same. It's actually more like 5,000. The Earth is more dense than water, so the Earth would not float in water, but Saturn might float in water because its density is not that much different from the density of water. So anyway, do this accurately and type the numbers with 3 or 4 significant figures into ln kappa. So that's one of the problems for next Tuesday. Here's another problem for next Tuesday. It's, again, it's a problem taken from chapter 1. It's problem 65 in chapter 1 about a horse race. In 1973, the Horse Secretariat, one of the greatest race horses in history, ran 1.5 miles in 2 minutes and 24 seconds in the Belmont Stakes. And part A is to calculate his average speed, expressed in standard or SI units. And then there's a part B, which I didn't copy here. So let's see how we're going to do this. We're going to calculate average speed. So we have to know what's meant by average speed. And again, it's explained in the chapter. Average speed is total distance divided by total time. So delta S stands for the total distance, and delta T stands for the total time. And again, it's another ratio. If you take the ratio distance over time, that'll be speed or velocity. The total distance divided by the total time gives you what's called the average velocity. It's not the instantaneous velocity. So in chapter 2, we'll learn about the difference between average velocity and instantaneous velocity. You know, as Secretary is running, sometimes he's running faster, sometimes he's running slower. He's not running with exactly the same speed for the whole 1.5 miles. You know, he starts out with speed 0. Then he speeds up, and then he's going faster. And then as he's coming to the finish line, he probably runs a little faster at the finish line, so he speeds up again at the finish line. So he doesn't have a single speed. He has a whole range of speeds. But the average speed means the total distance that he traveled divided by the total time that he took to travel that distance. Now here there's this delta notation. And the delta notation is used a lot in this course and in this book. If we have some quantity Q, which is a measurable quantity, it's a number. Delta Q means the change of Q. So Q is a variable. Q is something that changes. It's variable. It changes, let's say, from some initial value Q1. So you go from Q1, which is the initial value, and it goes to some final value, Q2. Delta Q is the change in Q. It's Q2 divided by Q1. You know, Q1 increases from, or Q rather, increases from Q1, that's a certain value, to Q2, that's a different value. If you take the difference, Q2 minus Q1, that's the change of Q. So delta Q represents a change of Q. Delta is not a number. Delta is an operation. You know, delta Q is not two numbers multiplied together. Delta Q is one number. It's Q2 minus Q1. Here it is. Delta Q is Q final minus Q initial. So delta Q is not two numbers, it's one number. It's two numbers subtracted. the first subtracted from the second. It's the change of Q. And we'll use the delta notation throughout this course. This is one kind of delta. This is where you have the average speed. You'll need the total change of Q. So this stands for the total change of Q. But we'll also need an infinitesimal change of Q to get the instantaneous velocity or instantaneous speed. So we'll come back to that in a future lecture or Zoom meeting. We'll also have a different kind of delta. We'll have the lowercase delta. The lowercase delta means an instantaneous, or rather an infinitesimal change. All right, but that's not relevant to this problem. This problem just concerns the average speed. So we need delta S, the final distance minus the initial distance. Well, the initial distance is 0 because he's at the starting point. The final distance, it says 1.5 miles. So that's the final distance that he's traveled, 1.5 miles. And we have, so delta S is 1.5 miles. It's a number with a unit. And now to divide by delta T, what's delta T? That's the time to go from the starting point to the ending point. Well, it's 2 minutes and 24 seconds. Now we're going to want to convert that into standard units. So let's write that as standard units or seconds. Let's write that as 2 times 60 seconds plus 24 seconds. That's 144 seconds. So this 2 minutes and 24 seconds is 144 seconds. It's the same thing. 2 minutes and 24 seconds is the same as 144 seconds. But we need to convert everything to the same units. So we can't do the calculation where we're using 2 different units. We have to convert it all to 1 unit. Might as well convert it to seconds because we want to express the answer in standard units. All right, so we're going to have 1.5 miles divided by 144 seconds. Now, again, we're going to have to convert the miles into meters. So to convert the mile, you have to know that 1 mile is the same as 1,609 meters. So mile is not a standard unit. Standard unit for length is meters. So you have to convert that 1.5 miles into 1.5 times 1,609 meters. Then we'll have meters in the numerator, seconds in the denominator. When we calculate the ratio, we'll get meters divided by seconds. That's the appropriate unit for speed. So here we've analyzed the problem. I didn't draw a picture, but I don't really need to draw a picture for this problem. I just have, it goes from here, 0, to here, 1.5 miles. What's 1.5 of 1,600? Half of 600 would be 800, and 16 would be 24. So this would be 2,400. Actually, more accurately, 2418. No, 24, a little more than 24. Let's say 2412 meters. So far, we haven't done any calculations. So far, we're just analyzing the problem. And that's the way most physics problems are. You're going to do a calculation eventually, but you don't do a calculation immediately. When you're ready to do the calculation, you pick up your calculator. So we have 1.5 times 1609 meters divided by 144 seconds. We see the unit, it's meter in the numerator, seconds in the denominator, so the units will be meters per second. And now you need your calculator finally to calculate this product and divide by 144, it's something like 17 meters per second. Now, you'll want to do it accurately with a calculator, but this is just kind of an estimate. Part B of the problem is to compare this speed to a different speed, and you'll do that. Okay, so that's two of the problems that I wanted to go over today. There's one more. Let me ask if there are any questions. Let's see on the chat. There are no questions on the chat. Does anybody want to just ask a question verbally? You just mute your microphone and speak up, either about problem set one or about anything else. Okay, then I don't hear any questions, so let me go on to the third problem. This is problem 1-86, which is a problem for the Flat Earth Society. Who measured the radius of the Earth? Well, first of all, who determined that the Earth is a sphere? Of course, members of the Flat Earth Society will say the Earth is not a sphere. The Earth is a flat, planar object. But of course, now we know the Earth is a sphere because we've seen pictures of the Earth from space. Well, who was the first person to understand that the Earth is a sphere and is not flat? Some people might say it was Columbus. You know, in the time of Columbus, there were people who believed that the Earth was flat because they had been not knowledgeable about science for a long time, and so they had the wrong idea that the Earth was flat. And so they told Christopher Columbus, "No, Chris, don't sail off to the west. You'll fall off the edge of the Earth. The Earth is flat." Of course, Columbus knew the Earth was not flat, but was a sphere, was round. And Columbus wasn't the person who determined that the Earth is a sphere. In fact, the fact that the Earth is a sphere was known long before Columbus. That was known to the philosophers or scientists of ancient Greece. In the secondary textbook, there's an example of how Aristotle knew that the Earth is round. And that was many years BC, the time of Aristotle. So even Aristotle knew the Earth is not flat; it's a sphere. But Aristotle didn't measure the Earth; he just said it must be round. Who measured it? Well, the first person to measure the radius of the Earth was a man named Eratosthenes of Cyrene. He was a Greek philosopher or scientist, astronomer from the time of the civilization or the empire of ancient Greece. He didn't live in Greece. He lived in North Africa. He lived in, I guess it was Libya, what's today Libya. Anyway, he lived in, or it might have been Egypt. Cyrene is the city he lived in. And he lived from 276 to 194 BC. So we're talking about hundreds of years before Columbus, many hundreds of years before Columbus, 200 years before AD, 200 years before the birth of Jesus of Nazareth. So this is way, way before the European Western civilization. And here's a hint on how to do the calculation. How did Eratosthenes determine the radius of the Earth? Well, by observing the sun. at noon in his hometown of Siren on the first day of summer solstice, the sun was directly overhead. And he had an assistant who walked north to another town quite a long ways away. And at the very same time, he observed the direction of the sun, and it was not directly overhead because the sun was over here. Oops. The sun was over here, far, far away. Far away. And so the direction of the sun was perpendicular to the surface in Siren, but not perpendicular to the surface where his assistant was. Now, his assistant knew the distance between those 2 points because his assistant measured the distance from Siren to the nearby point, not so near. He had to walk many, many miles. So that distance that was measured by his assistant, we could call that S. And the difference of the angles between the directions of the sun is this angle right here. Let's see if I can draw this. Let's see. I don't know if I can draw this. So use a bit of trigonometry here. So here was the direction of the sun measured by his assistant. And here was the angle. The difference between this angle and this angle would be, or rather the distance between the center of the Earth and this point, the perpendicular to the Earth and this point. This is already perpendicular to the Earth. This is not perpendicular to the Earth. If I extended it further towards the center of the Earth, it would not reach the center of the Earth. And that angle, I don't know if I can draw it, that angle I'm not having too much luck here, am I? It's this angle right here. It's this angle right here. That angle. And that's the same as this angle. So this is the angle theta. So you see, here's a measurement of S, the distance, and here's a measurement of theta, the angle. And now, if you measure theta in radians, then S is the radius times theta. For example, if you went all the way around the Earth, the distance would be the circumference of the Earth, 2 pi r, and the angle all the way around the Earth in radians is 2 pi. If it's a fraction of 2 pi, it's some amount theta, it's that fraction times r, which gives you the distance on the circumference. So S is r theta. That's the definition of theta if you use radians. Now, if we use degrees, then we divide 2 pi radians, the full circumference, by 360. There's 360 degrees in a full circle. So 1 degree is 1 over 360 of 2 pi. If I write this equation out in words, S is the arc length. It's the arc length on this great circle. R is the radius. That's what Eratosthenes was trying to measure. Theta was the angle. That's what his assistant determined by comparing the direction of the sun and the normal to the surface. All right, so that's how Eratosthenes measured the radius of the Earth. And actually, the value that he got is pretty close to a modern value. So he got a pretty good value, considering that all of this was done, 200 years BC. Now, let me end the recording. We'll stop the recording.